Okay, so in the last lecture and the lecture before that, we were looking at linear and affine functions. And more specifically, we learned what these things are, and then we learned how we can use affine or linear functions to model data. And it seems somewhat strange that we would choose linear functions to model data that is probably not linear in nature, not affine in nature. But the reason why we do this comes down to what's called a Taylor approximation. So that's what we're going to look at today. And this will be relatively brief, a relatively brief discussion, but it's definitely something that I feel warrants its own recording, own lecture, because it's such a useful idea in applied mathematics and in data science, because yes, there are complicated models for making predictions in data science now. There are deep neural nets, there are support vector machines are linear in nature. But these deep learning things are highly complex prediction functions. But in practice, when you're working for a company or consulting, in what I've experienced, most things you can more or less get away with making linear approximations with. Okay, so I'll just write that down. Actually, it's like my first bullet point. So in many instances, for many applications, I suppose, scalar value functions in variables, the general functions that we've been learning about, can be approximated as linear or affine functions. Right, and if we think back to linear regression that we did last time, the model that we built was a linear approximation to the data, and the data was not linear, it bounced around a lot, but it was good enough. Okay, so basically, what am I trying to say? I'm trying to say that linear models are not only the best model to start with, but will actually probably be the one that works more often than not. So linear models are important. I'll just say that. They're simple yet important. They're the most simple model that you can build in many cases, but that doesn't mean that they're not useful. So let's kind of talk about why it would make sense for a nonlinear function or non-affine function to be approximated by one. So to keep life simple, I'm going to draw a function of one variable. Okay. So, and this is, just imagine that this function, this data that's generating this function that's like non-linear, right? So more or less, let's suppose that like the function, the true like perfect function looks something like that, and that the data is like close to this function. And the data that, well, maybe we don't have any negative values, maybe it's just like And these little notches just represent the data that we observe. And like the true function is something like this. Okay. But more or less, like we have some data that's generating a function, and we observe that, for example, here, like if this is like z right there, we can approximate this function maybe here. Where is that point? So like, there's a linear function modeling the line tangent to that graph right there. And we see that close around z, that more or less they're the model, the linear or affine model, is basically good enough, right? And even if it wasn't like that great, the closer we are around z, the more likely it is that we're going to be tight around the model and the actual function, which in many cases, this function is not known in many cases. Okay? And then like maybe this is like maybe there's like another like z1 right here, and we want to model the data around that, around z1, then we can more or less make another function, and then we see that around z1, they're basically matching up. Okay. So for these linear approximations around a input number, right? What do we really want? We want our approximation to satisfy a few things. So we're going to say f hat of x denotes our affine approximation to f. We're just going to use that notation. Right, so we want that to be close to the function around a given point that we put in. So for now, let's maybe focus on this z right there, just to make life a little bit easier. So in particular, there's one thing that like we really want. We want the function and the model to match up at z. So what do we want? We want the approximation at the value z. We want that to equal the actual function at z. Okay, and that like lies right on the graph. We can do this in a lot of cases. So that's not a hard one to impose. The second thing that I want to illustrate, or not illustrate, to point out is that the slope of this line, the derivative of the approximation, isn't it the same as the derivative of the white function at that point? They both have the same slope at that point at z. So what we want is that we want the derivative of our approximation to equal the derivative of the true function at that value. If we can construct a function that does this at this value z, then we would have a linear or affine approximation to the true white function here with the blue one around that point z. Maybe not like overall, but around z, it's more or less the same thing. Okay. So to do that, in this case, we can say, aha, let's make our model equal to the following sum. Like that. So if this is our function, does it satisfy 1 and 2? Well, if we plug in, so the question is, does this satisfy these two things? Do they match up at the value z, and do their derivatives match up at the value z? Well, if I plug in z, well, that's just a number, right? That's just the true function's value at z. And then here we have z minus z, which is 0 times a number. Okay, it matches up with part 1. Okay. So yes, this one does match the first thing that we want. What about the second thing? Well, if we take the first derivative of this function, that's a number, that goes away to 0. So that goes away. And then here, the coefficient of x is this number, and z is just a number, so that goes away, and we're left with f prime of z. So it satisfies part 2 as well. Okay. So this here is our affine approximation. This is, and people will refer to this as, so this guy right here. So this is a first order linear approximation. It's really an affine function, but people call it linear. First order linear Taylor approximation for x around z, around the input number z. X around z. Okay. And I'm going to make a homework problem for you where you actually will try to plot these things out and see that this first order Taylor approximation is really good around z. It's as good as like you in most cases that you'll want, unless your original function is highly non-differentiable. But this is just for a function of one variable. What we really want is a function for n variables. And as before, when we were looking at functions of n variables and we wanted to understand how the output changes when we take a step in this direction and this direction, which we needed the gradient to do that, we're going to have to look at partial derivatives to understand how to make a affine or linear approximation to these things. But it's not difficult. So let's just say that let f be a function of n variables. So let this be a differentiable function, meaning that the gradient exists. And then let z be some point in the domain, or some vector in the domain. So z is just some n vector. Okay, here z was just a number, here it's an n vector. Okay, so the first order Taylor approximation of f near z. Again, I have to emphasize that near that input z is f hat of x equals to f of z, just like before, because this is just some scalar, right? This is a scalar valued function plus the derivative in the x1 direction at z times x1 minus z1. Remember, there's going to be n components plus dot 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 plus the n the derivative with respect to the n component at z times xn minus zn. And this is just the more general version of this. This is like when there's only one variable, but here now we have to take into consideration every direction, right? And what will happen is that this is the same idea. For the original function, f at z is going to equal this because all of that goes away. Like all those components go away. Okay? And then the partial derivatives for this function will match up with this because everything else will be zeroed out except for the one in question because of how we've designed it, just like we did over here. So the gradient at z is the same for this function, and the function's values at z are the same. So this is the general approximation where that was just like the one variable approximation over there. Now, this is annoying to write all this out, right? This big plus, but we see that it looks like, oh, we can maybe write this as a inner product, and we can. So the mature way to do this, the way that we should write this out is going to be like this. There. So then you'll see this inner product is precisely this, because what are the elements of the gradient? They are the partial derivatives. And if you plug in z into those partial derivatives, you'll have exactly that. So it's the same. Okay. So let's go ahead and work through the example they have in the book using this first order approximation. So let f map R2 to R, so function of two variables, be defined by f of x equals to x1 plus e to the power x2 minus x1. Okay, and then it says find the Taylor first order Taylor approximation of f near the vector z equals to 1, 2. Okay. So in order to do this, we need to find the gradient first. In order to do that, we need to find the partial derivatives of this function with respect to both the variables. So if dx1 is just 1, and then now derivative of this with respect to x1 is just coefficient, so this would be minus e to the power x2 minus x1. Take the derivative of this with respect to that variable, you get derivative of that is minus 1 times this, so that's why it's that way. And then df of x2, that's going to be, so 0, and then just that. And notice that each of these is a function of two variables, so we can plug in something. So we're going to plug in z equals to 1, 2 into both of these to get the gradient. So this will be 1 minus e to the power x2 minus x1, so x2 minus x1, so just 1, right? I think I did that right. And in the next entry, it's just going to be e to the power 2 minus 1, so just e. Oh, and these have like numerical values, probably useful. It's just like negative 1.718, and then here it's 2.718. Okay, so that's your gradient evaluated at that vector z. So then the first order Taylor approximation is going to be the function f of x equals to f of z plus gradient at z times x minus z. So what's f of z? So f is here. So 1 plus e to the power 1. So f of z, 1 plus e to the power 1. So it's going to be that plus 1. So it would be 3.718. For that one right there. Plus this inner product. So this times that. So maybe I'll just write it out like that. So negative 1.78 and then 2.78 times z, and z was 1, 2. Okay, so then this will be 3.718. Oh, what am I doing? X minus z. So this is going to be x1 minus 1 and x2 minus 2. So this is x minus z, there's the gradient, and there's f of z. All right, so it's going to be that times that. So it's negative. So I'll just go ahead and put the negative there. Negative 1.718 times x1 minus 1, and then plus that times that. So 2.718 times x2 minus 2. There's your function. Okay. Now there's a nice little table in the textbook that shows that this function here, this is our approximation, our model. It basically, for values of input close to that z, it's basically the same thing. Hopefully all of you can read that. So what does the table look like? I'll just put down 3 entries. X, the true value, our model, and the error. So f hat of x minus f of x in absolute value. So that's like how far off our guess was, or our approximation was. So when x was the vector 1, 2, we see that 1 minus 1 is 0, 2 minus 2 is 0. It's just that. But that's also the value for f at 1, 2. So it's just going to be 3.718, 3.718, and then that minus that in absolute value is 0. Okay, so what about the vector 0.16, 1.98. So that vector is really close to that vector. And yeah, you can see that. So then if we plug this into the original function, we get 3.7332. If we plug that vector into this function, we get 3.7326, and then that minus that in absolute value gives us 0.0005. So that's our error, and that's a tiny little error, right? So, and if you perturb anything, like just add a little bit to this, subtract a little, just find a vector close to this one in the components. And if you plug it into the approximation and you plug it into the original function, you'll see that the values that they output are basically the same. And it's because around z, small enough values around z, like perturbations around z, it's basically a linear function around z, around a little neighborhood. In a neighborhood around z, sorry. Okay. So this is a really nice idea, and it has many applications that hopefully we'll be able to get to one of them at least this semester. But I guess the key takeaway is that linear functions are powerful approximations to pretty much any function that you come across. Okay. All right, so that'll be it for this recording. I'm going to go ahead and stop the video now.